Okay, welcome to the last lecture of this semester, and I know we're all excited about that. I appreciate those of you that have hung in with me throughout all of this. It's not been a typical semester for anyone, and I do appreciate the effort you've put into the class. So today I wanted to cover a section. I'm going to skip ahead a little bit to section 7.4 and maybe even take an example or two from section 7.5 because especially for those of you going into calculus, you need some experience with solving basic trig equations, and that's what we're going to look at today. If you have your unit circle with you, I would suggest getting that out. I think it'll be helpful as we go through this. Okay, so we talked a little bit last time about the difference between an equation and an identity, and we worked mostly with identities, and that is equations that are true for every value of the variable. But today we're going to be looking at solving some. So this one's true for everything, but then these we can actually solve, and we're going to look at how we can solve these type equations. Okay, so the directions are going to say something kind of different. They're going to say find all solutions of the given equation. But because of the periodic nature of our trig functions, we can't technically write down every single solution because every time we go around the unit circle, we're going to pick up another set of solutions. And we can go around that unit circle infinitely many times. So we can never physically write down every single solution. But there is a way that we can write an expression down that's going to cover all the solutions. So if we're working with the function sine, cosine, cosecant, or secant, because their period is 2 pi, we can find all the solutions from 0 to 2 pi and then simply add plus 2 pi k. And what that does is that's going to pick up the solutions every time you go around the unit circle. That's our notation for doing that. So if k is 0, then we're going to get the solutions that are on the basic unit circle from 0 to 2 pi. If k is 1, then we're going to get the ones for the next rotation and so forth. If you're working with the trig functions tangent or cotangent, their period is pi. So instead of writing plus 2 pi k, we're simply going to write plus pi k because of the difference in the period, because we know that they repeat every pi units instead of every 2 pi units. Okay, so a few strategies I kind of wanted to summarize here for you before we get started. First of all, we want to always start by isolating the trig function. So get that trig function by itself, regardless of what it is, whether it's sine, cosine, tangent, get it by itself. You'll take the inverse of the trig function, and I have a typo here. Take the inverse of the trig function to solve for the angle. Determine the quadrants in one period that would satisfy the equation. Now, some of these you're not actually going to have to take the inverse trig function because they're going to simply be on the unit circle. But if it's a decimal and it's not on the unit circle, then you're going to need to take the inverse trig function. Okay, so determine the quadrants and then find all the solutions in those designated quadrants. Okay, and that's going to mean that you're going to end up having to find your reference angle and make sure that you're placing it in the appropriate quadrants. And then the last thing, like we just mentioned on the previous slide, if you have sine or cosine or and cosecant and secant are going to go along with those, then you're going to add plus 2 pi k. And if you have tangent, you'll add pi k to that. Okay, so in the first quadrant, just as kind of as a review, the first quadrant angles are their own reference angles. In the second quadrant, if we want to place an angle over here, we're going to do pi minus the reference angle, pi plus the reference angle, and then 2 pi minus the reference angle. All right, so looking at this one, we're going to solve the equation sine of theta equals 1/2. So we've kind of done this before. We're looking basically at the unit circle and trying to decide where is the y coordinate 1/2. So we know that that happens at the square root of 3 over 2 1/2, and also over here at negative square root of 3 over 2 1/2. And those are going to be, this would be pi over 6, and this is going to be 5 pi over 6. So our solutions would be pi over 6 and 5 pi over 6. That's going to represent the answers or the solutions for one revolution about the circle. But because in this section we want to give all answers, we're going to consider if we were to keep going around this, every time we go around this circle and we hit this location, we're going to pick up another solution. And every time we hit this location, we're going to pick up another solution. So they're just going to keep coming So rather than writing every single one down, which we can't physically do, we're going to put plus 2 pi k beside these. And I'll write this a little bit better down here. So we've got pi over 6 plus 2 pi k, and we've got 5 pi over 6 plus 2 pi k. So we want to find all the solutions on the first rotation around the unit circle, and then put the plus 2 pi k to account for all the additional times around. And this is just showing you, like, here's one revolution or one cycle of the one period of the trig function, and here's another one, and they just keep repeating. And so here's a line at 1/2, and you can see that we pick up one set of solutions, another set of solutions, and so forth. And so that's why we have to put the plus 2 pi k for that. Okay, here we have sine is equal to negative 1/2. So sine's going to be negative 1/2 here, and also here. So at 7 pi over 6 and also 11 pi over 6. And again, so we can account for all our solutions, we're going to put plus 2 pi k beside each one of those. So not too difficult with that. Okay, here's one where you're actually asked, instead of listing all solutions, which is where you put the plus 2 pi k, you're going to be asked to list 8 specific solutions. So if we look at this, we're looking for where cosine is negative 1/2. Well, cosine is negative in the second quadrant and also in the third quadrant. So in the second quadrant, cosine is negative, I think I said negative 1/2, but negative square root of 2 over 2. So that value is going to be 3 pi over 4. And the other place is in the third quadrant, and that is going to be here at 5 pi over 4. Okay, so basically what we would have is 3 pi over 4 plus 2 pi k and 5 pi over 4 plus 2 pi k. Okay, so here with 3 pi over 4, we're going to be adding 2 pi k to it. So for the first one, if k is 0, then we're just going to have 3 pi over 4, and we're going to have 5 pi over 4 when we put 0 in for k in each of these. If k is 1, then I'm going to have 3 pi over 4 plus 2 pi. And that's going to, if you want to put that in your calculator, leave the pi's off and do 3/4 plus 2, and then convert that back to a fraction, and you're going to have 11/4. So 11 pi over 4. Over here, if we do 5 pi over 4 plus 2 pi times 1, or just 2 pi, then same thing, 5/4 plus 2 is going to give me 13 pi over 4. Okay, if I do k equals 2, then I'm going to keep going with this. So 3 pi over 4 plus 2 pi times 2, because k is 2, and that's going to give me 19 pi over 4. And if I do 5 pi over 4 plus 2 pi times 2, that's going to give me 21 pi over 4. Okay, and we can do these in the negative direction as well. So if I wanted to do k equals -1, then that's going to be 3 pi over 4 plus 2 pi times -1. And if I simplify that, I'm going to get negative 5 pi over 4. If I do 5 pi over 4 plus 2 pi times -1, then I'm going to get negative 3 pi over 4. So I can do all different k's. I could keep going with k equals 3, k equals 4, k equals 5. I could do k equals -2. It just depends, but you're asked a lot of times for the directions on WebAssign to list 6 or 8 specific solutions. So here my 8 specific solutions will be these basic ones from the unit circle, and then I'm going to get these others that I pick up for each revolution around it. When you're putting these in your calculator, and you're starting with some from the unit circle like this, always leave the pi part off and just put in like 3 over 4 plus 2, and then put the pi beside it. Don't try to incorporate the pi into the calculation because you're going to get a decimal that will not convert back to a fraction, and your WebAssign is not going to like that and is going to count it wrong. Okay, so here's another one, solving for tangent of theta equals 2. So here we don't have a place on the unit circle that we're familiar with where tangent is 2. So this is one we are going to have to do the inverse tangent of. So if we look at this, the inverse tangent of 2 is going to be approximately 1.12, and this is in radians. Everything we're doing today is in radians, so 1.12. And if we're giving all of our solutions, which we are in these examples, we're going to do 1.12 plus pi k, and that's going to take care of all of our solutions. Remember, tangent has a period of pi, so instead of doing plus 2 pi k, we just do plus pi k. And also remember that this would be a solution here in the first quadrant. Tangent is positive in the first and third quadrant. So if we go halfway around, which is what pi is, then it's going to put us down here in this third quadrant. If we go pi again, we're going to be back up here in the first quadrant, and we're just going to keep doing that, picking up solutions in the first and the third quadrant. And this is just a representation here. Here you see between negative pi over 2 and positive pi over 2, we get one solution, and then if we add pi to that, we keep getting these other solutions. If we take pi away, then we get solutions going in the negative direction. Okay, here's another one with cosine that's not on the unit circle. So this is one that we would need to do the inverse of. So we'll do the inverse of 0.28. So our theta on this one is going to be 1.287. We have to be a little bit more careful than on the tangent, simply because there are two quadrants where cosine is positive. That's going to be here in the first quadrant and in the fourth quadrant. So this has given me my answer in the first quadrant. It's going to be 1.287, but I don't know what the one in the fourth quadrant is. If you remember, in the fourth quadrant, you always do 2 pi and take away your reference angle. So this is the reference angle here, because remember, your first quadrant angle is always your reference angle. So my other answer then is going to be 4.996, and just follow the directions in WebAssign as to the rounding on these. So the first quadrant one is 1.287, and the second quadrant one, fourth quadrant one, is 4.996. So that's the basic ones for the first time around the unit circle. From there, we've got to find all the others. So since everything is in decimals here, what we're going to do is we're going to have 1.287 is one of them. The next one, we're going to do 1.287 plus 2 pi. This would be the k equals 0 case. So this is going to be the k equals 1 case. So when I put that in and get an entire decimal answer for everything, I'm going to have 7.570. And then if I do 1.287 plus 2 pi times 2, I'm going to have 13.853. Okay, if I do the 4.996 and I add 2 pi times 1 to it, I'm going to get 11.279. And then if I do 4.996 plus 2 pi times 2, I'm going to get 17.562. If you needed more specific solutions, you could keep going. You could do k equals -1 and get some negative answers. So you don't, these are not, there's some variability on the answers that will be accepted. So there's lots of answers out there. It's just asking you to give 6 specific ones. It doesn't really tell which 6. So here are the 6 that we're given. These values here should satisfy that equation. If you're ever unsure about whether your answer works, just simply take it and plug it back in. So if I take the cosine of any one of these values here, I should get 0.28, or just because of rounding, it might be something like 0.279 something. So as long as it's pretty close to 0.28, then that's just a rounding issue. Okay, so here's another one we're going to look at for the tangent. So we'll have theta equals the inverse tangent of negative 10. So theta on this one is going to be negative 1.471. Okay, so we know that tangent is negative in the second and fourth quadrants. Okay, so this is a negative here that it's given me. So it's actually giving me the answer down here, negative 1.471. So what I can do with that is I can take that and understand that there's going to be one over here as well. I could go ahead and find that one if I wanted to, but it doesn't really specify that the first one has to be between 0 and 2 pi. All we really have to do is do negative 1.471 plus pi k in this case, because the period of tangent is just pi, and this is going to be my answer here. Okay. That's going to be my general answer. And then for my specific ones, I'm going to take and look at different k values for this. So if I do k equals 0, I'm going to have the negative 1.471. If I do k equals 1, then I'll have 1.670. I'm just putting 1 in here and getting a decimal answer for that. K equals 2 would be 4.812. K equals 3 is going to be 7.953. K equals negative 1 will be negative 4.613. K equals negative 2 is going to be negative 7.754. And that should be 6 of them. We could go on in either direction till we get what we need, but this would be my general expression for all the solutions, and these would be 6 specific ones that I should Okay, moving on to some others that are slightly more complicated. On these, you want to isolate the trig function first, so I want to get everything else away from it. So that means I'm going to move the 1 to the other side, and then I'm going to divide by 2. So I'm going to get the sine of theta is 1/2. So thinking about my unit circle, I want to figure out where sine is positive 1/2. Sine is positive in the first and the second quadrants. So, and sine is 1/2 for my pi over 6 angles. So that means in the first quadrant it would be pi over 6, and in the second quadrant it's going to be 5 pi over 6. So I'm going to do pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. So it's actually an easier problem when it asks for all solutions than it is to ask for specific solutions. Okay, here's another one. And again, at any point, if you feel comfortable, you can try these yourself. So at any point, you can always pause the video and try the problems to see how you do with them, and then check your work. So on this particular one, again, we're going to get tangent by itself. So I'm going to have tangent of theta is 3. Just move the 3 to the other side. Actually, tangent squared of theta is 3. We'll take the square root, and we'll get tangent of theta is plus or minus the square root of 3. Hopefully you recall that the pi over 3 type angles are the ones that have a tangent that is the square root of 3. So what we have to do is we have to figure out which ones are going to satisfy that. So if I look at this, tangent is positive in the first and third quadrants, and it's negative in the second and the fourth quadrants. So what's happening is we get a lot of repetition around here. So in the first quadrant, we would have pi over 3. And if we wanted to look in the fourth quadrant, we would have negative pi over 3. Because if you remember, usually when we do inverse tangent, then we are restricted to the fourth and first quadrants here. So we would do negative pi over 3 plus pi k and positive pi over 3 plus pi k. Sorry, not pi over k, pi times k. So a couple things here. There are alternative ways to write this. So instead of writing negative pi over 3, we could have actually put 2 pi over 3 would have been an option. We could have written this as 5 pi over 3 and it would have still worked. So there's multiple ways that you can express these, but these would be the most logical. Again, tangent has a period of pi, so we put plus 2 pi k, sorry, plus pi k instead of plus 2 pi k. Okay, here's another one. Again, if you feel comfortable, try it. So we want to get cosine by itself. So we'll start out by moving the 1 to the other side. Then we'll divide by 2. So we're going to get cosine squared is equal to 1/2. We'll take the square root. So we've got cosine of theta is plus or minus, and this would be the square root of 1 over the square root of 2. Square root of 1 is 1. And if we rationalize this, what we're going to have is the square root of 2 over 2, because the square root of 2 times the square root of 2 is 2. So basically, we're looking for where everywhere on the unit circle that cosine is either positive or negative, square root of 2 over 2. So if we think about our unit circle, cosine is positive in 1 and 4, and it's negative in 2 and 3. And the pi over 4s are the ones that give us a cosine that's the square root of 2 over 2. So basically, we want to find all of these different values here. So we're going to have pi over 4. We'll have 5 pi over 4. We'll have, sorry, I skipped 3 pi over 4. And we'll also have 7 pi over 4. So this is the first quadrant, second quadrant, third quadrant, and fourth quadrant angles with that. And so from here, what we can do is we can do plus 2 pi k for each one of these. And we'll get our answer there. Okay, here's one for you to try. Okay, if we subtract 1 from both sides, we'll get a negative 1. Divide by the square root of 2. We've got the sine of theta is negative 1 over the square root of 2. We rationalize that denominator like we just did for another problem. We'll have negative square root of 2 over 2. So our problem is sine of theta equals negative square root of 2 over 2. So we're looking on our unit circle to find the places that sine is negative. So sine is negative in the third and the fourth quadrants. And the type angle that gives us a sine that's the square root of 2 over 2 is going to be our pi over 4s. So in the third quadrant, that's going to be 5 pi over 4. And in the fourth quadrant, that's going to be 7 pi over 4. So we're going to have 5 pi over 4 plus 2 pi k and 7 pi over 4 plus 2 pi k. Okay, so factoring is a useful technique when it comes to solving trig equations as well. So some of these next examples, we're going to be taking a look at factoring as a method for solving trig equations. Okay, the first one here, we've got 2 cosine squared theta minus 7 cosine theta plus 3 equals 0. So what I would suggest doing in order to factor this is to convert it and just put x's in the place of the cosines and factor this. So if we factor this by the bottoms up method, we're going to multiply these two together. So we'll have x squared minus 7x plus 6. So this is going to factor into x minus 6 and x minus 1. And then we want to go back and divide by our leading coefficient. So we're going to have x minus 3 and x minus 1/2. So once we've got it factored, now we want to substitute back for the x and put the cosine back. Okay, so we're just simply replacing cosine with an x and then putting that cosine back. So now, since this is set equal to 0, I want to set each factor equal to 0. And these actually should be thetas instead of x's. So we'll have cosine of theta minus 3 equals 0, and cosine of theta minus 1/2 equals 0. So cosine of theta would be equal to 3 in this one, and cosine theta would be equal to 1/2 here. This one is not going to give us any solutions because cosine never goes up to 3. Over here, cosine is going to be 1/2. If we think about this, cosine is positive in the first and the fourth quadrants. So cosine is going to be 1/2 for our pi over 3 angles. So we're going to have 5 pi over 3 and pi over 3. So those are going to be our two solutions. And we just need to write it as pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. Okay, here's another one. If we factor this, we've got, I'm going to replace the cosine with an x. So 4x squared minus 4x plus 1 equal to 0. If I do this by the bottoms up method to factor it, and this is a good time right before exams to review the bottoms up method. So I'll multiply those together and get 4. So I'm going to have x squared minus 4x plus 4 equals 0. So this is going to factor x minus 2 and x minus, sorry, this should be a plus 4. I think the the pen took my mark off there. So we've got x squared minus 4x plus 4, and this is going to factor into x minus 2 and x minus 2. Okay, so we want to be sure that we divide here for the bottoms up by the leading coefficient. We'll reduce and then do the bottoms up. And then we're going to substitute back. Okay, so these are both the same, so I don't really have to set both of them equal to 0 because I'm going to get the same solutions from them regardless. So I'll have 2 cosine of theta equals 1. Cosine of theta is 1/2. And I think that's the one we just finished solving here on this previous one. We had cosine of theta was 1/2. So we're going to get the same solutions here. We're going to get pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. Okay, here's one that if we could do a different type of factoring instead of a trinomial, we could just factor out a GCF. So we'll have cosine of theta times 5 sine theta plus 4, just factoring out cosine as a GCF. We want to set each factor equal to 0 and solve. So cosine is 0. Think about your unit circle. Cosine is going to be 0 here and here because our coordinates are 0, 1 and 0, -1. So that's going to be pi over 2 and 3 pi over 2 for those solutions. Over here, we've got 5 sine of theta equals -4. So the sine of theta is going to be -4/5. So this is not on the unit circle, so I'm going to have to do the inverse sine. Okay, when I do that, I'm going to go ahead and get a decimal answer for it, and it's going to be -0.427. Okay, if you recall, inverse sine, we only get answers in the fourth quadrant and the first quadrant. So if it's a negative, then this is coming here from the fourth quadrant. But sine is also negative over here in the third quadrant. It's just our calculator's not going to give us that when we do the inverse sine here. So I've got to find this other angle over here. And this is where my reference angles are going to come in. This one, this negative angle here actually has a reference angle that is equal to 0.927. So if I come over here and do pi plus 0.927, that's going to give me 4.067, and that's going to be here in this third quadrant. So my answers on this one are going to be negative 0.927 and 4.067. So I'm going to take these that I picked up from the first and these from the second and put plus 2 pi k and be finished with my answers. One thing here you may have noticed, since this is exactly halfway around, these two combined could be equivalent to saying pi over 2 plus pi k, because every time you go pi around the circle, you're going to get one of our answers. So there are occasions where two can be combined into one, but I'm not necessarily expecting you to pick up on that. If you can get these without getting that, I'm okay with it at this point. Okay, here's one for you to practice with the GCF. So I have cosine of theta is going to be sine of theta minus 2. So set each factor equal to 0. So we get cosine is 0 at those same places, pi over 2 and 3 pi over 2. Sine is not going to equal 2 anywhere, so we don't get any solutions there. We'll have pi over 2 plus 2 pi k and 3 pi over 2 plus 2 pi k. Okay, we have two more examples that I want to get through, and these involve what's called a multiple of an angle. So these are the ones where we have a k in here besides 1. So they are done slightly different. So I want to go through just a couple of these. The first one that we're going to look at, we've got 2 sine of 3 theta minus 1 equals 0. So we want to go ahead and solve for sine of 3 theta. So that means we're going to move the 1 to the other side and divide by 2. Okay, so we've got sine of 3 theta equals 1/2. So if you remember, what this k tells us is it tells us the number of complete sine graphs that we see between 0 and 2 pi. So if I'm seeing 3 sine graphs between 0 and 2 pi, and I get 2 answers every time I go around, for every cycle of pi, I get 2 times that sine is equal to 1/2, then I'm going to have 6 total answers here. So what I'm going to do is I'm going to start out and I'm going to write this out. So the sine is 1/2. Okay, sine is positive in the first and the second quadrants, and that's going to be the square root of 3 over 2 1/2. So that is my pi over 6 angles. Okay, so I'm talking about a pi over 6 and a 5 pi over 6. Okay, so I'm going to go ahead, and that's the first time around. So I'm going to go ahead and look at these. If I were to do plus 2 pi k. Okay, so if I had pi over 6 to start with, and I go around another time, I'm going to be at 13 pi over 6. And then if I go around again, which is adding another 2 pi to it, I'm going to be at 25 pi over 6. If I start here at 5 pi over 6, go around a complete time, I'm going to be at 17 pi over 6. And if I go around another complete time, I'm going to be at 29 pi over 6. Okay, so that takes care of like the 3 cycles here. The only thing I've got to still do is I need to actually go back in and divide each one by this number here in front of it. So I'm going to divide each one of these by 3, which is going to change my denominator from being a 6 to being an 18. So I'm going to have pi over 18, 13 pi over 18, 25 pi over 18, 5 pi over 18, 17 pi over 18, and 29 pi over 18. So those will be my six, or that would be all the solutions in this interval from 0 to 2 pi. So we basically answered part B first. So part A, where I'm finding all the solutions of the equation, I'm going to go back to this where I had pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. And I'm going to divide all of this by this k here. So my k was 3. So I'm going to divide that by 3. And I know it's a little bit confusing because basically our book uses k for two different things. So this k is not the same as this k here that I'm referring to. So this is going to simplify to be pi over 18 plus 2 pi k over 3. And this is going to be 5 pi over 18 plus 2 pi k over 3. So these would be the general expression for all the solutions, and these would be the solutions on this interval from 0 to 2 pi. Granted, this is the most confusing one. We're definitely ending with the hardest material, but it is something I wanted you to at least see before we concluded this semester. Okay, let's look at one more example like these. Okay, so we have this one here. I'm going to start, and I've got 2 sine of 2 theta equals 1. So the main difference here is that this is a 2 instead of a 3. So we'll do 2 sine of 2 theta equals 1/2. Sorry, I'm going to step ahead of myself. Equals 1. Then we'll divide by 2, and we'll get the 1/2 I was writing. Okay, so here we want to know where sine is 1/2. So we already went through that and said sine is positive in the first and the second quadrants, and that is going to be the case for my pi over 6 and also my 5 pi over 6. Okay, so I would have pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. All right, so pi over 6 and 5 pi over 6, that's representing the first time around the circle, but I know that I've got to go, there's 2 complete cycles between 0 and 2 pi. So that's the first cycle, and the second cycle I'm going to add 2 pi to this. So if I add 2 to 1/6, I'm going to get 13 pi over 6. And if I add 2 to 5 pi over 6, I'm going to get 17 pi over 6. Okay, I only have to do 2 cycles this time because there's a 2 here. All right, so to finish this up, I'm going to divide each one by 2 because that's the value here in front of my theta. So my answers are going to be pi over, if I have a pi over 6 and I divide it by 2, that's the same thing as a pi over 6 times a 1/2. So that's going to give me a pi over 12. So this is going to be pi over 12. This will be 13 pi over 12. This will be 5 pi over 12. And then 17 pi over 12. So those are the solutions on the interval from 0 to 2 pi. So that's part B. Part A, we're going to go back to these expressions and divide them by 2 as well. Okay. So I'm going to have pi over 12 plus, if I have 2 pi k divided by 2, my 2's will cancel, and I'm going to have pi k. And then here I'm going to have 5 pi over 12 plus pi k. And that takes us to the end of what I want to cover, not just in Chapter 7, but in the course. So the remaining time we will be getting ready for your final exam and wrapping up the semester. So please let me know if I can help you with anything that you're encountering in this chapter or reviewing for the exam, and I hope you have a good day.